Hi everyone, welcome to my video number 7. Alright, for this video I will talk on triple integral. Okay, triple integral. Now in the previous video we have seen, I think, for the single variable case or single integral, double integral, I have discussed in quite detail. Now I'm going to focus on the triple integral. Now let's say we have rectangular box. Okay, let a rectangular box so let's call that E, given as say AB, CD, RS. This is for X, this is for Y, this is for Z. So if we sketch this, it look like this is X, Y, Z. So we have X from A to B, and Y from C to D, Z from R to S. This is Z R to S. Okay, so what I'm going to do is trying to plot those rectangular box. So we have those, right? And then we have that, some more. Okay, so we have this, we have that, we have one more, B, no, that, all right, that and that, and we have that. So as you can see, so this is our rectangular box. That, okay, where is it? Okay, so we have this rectangular box, this that, okay, that's okay, so that is rectangular box bounded by that. So this is our E. That's E. Now we want to integrate a function f. Let's say given a continuous function f of 3 variables x, y, z. Okay, now if I integrate this over region E of x, y, z, dx, dy, dz. Okay, integrate this. So your dx is from A to B, your x is from A to B, your y is from C to D, and your z is from R to S. Okay, So this is what we call integrate over the region E of f dv. So that gives us that. So this is what we call as a Frobenius theorem. Frobenius theorem. Frobenius theorem, basically we have three form. This is the first form. This is the first form. This is the first form, and you can of course rearrange the integration. Either you want to do it iteratively x first, y or z, or you can also have for example, you want to integrate with z first. So probably you can put the outer integral as x. So you can put ab here, cd here for z rs, then your fx, y, z. This is dz, dy, dx. You can just interchange because the boundary of the box is just a just on a straight line, so that you have no problem there. Okay, so let me give you example. Let's say example, you want to evaluate E, the function given as x, y, z squared dv, where your E is given as all point x, y, z, such that x in 0, 1, y minus 1, 2, and z is 0, 3. Okay, now to evaluate those integral with this boundary, okay, then that equal to x from 0 to 1. You can put this here, x from 0 to 1. If I want to evaluate the innermost integral x, then I put x there. Then our y from minus 1 to 1, y from minus 1 to 2, and z from 0 to 3, z from 0 to 3. Our function is x, y, z cube dy. Sorry, d. So dx, dy, dz. So dx, dy, dz. Okay, so first we integrate with respect to x, then integrate with respect to y, then integrate with respect to x. Okay, so let me finish this. This is z from 0 to 3, y from minus 1 to 2. Now we integrate with respect to x, which means y and z are constant. So with respect to z, so we have x, so we have x squared over 2 y z cube. The value for z, limit for x 0 to 1, so that's, then we have dy dz. Okay, simplify this. What we have, 1 over 2 y z cube minus 0. Okay, 1 over 2 just constant. I can factor out that, so that gives us half z from 0 to 3, y from minus 1 to 2. So what left is that y z cube dy dz. Now we integrate with respect to z. We integrate with respect to y. So we have half z from 0 to 3. So we have y squared z cube over 2 y from minus 1 to 2 dz. Okay, so what you have inside there, this is 4 over 2z cube minus half z cube. Okay, then you can solve for z. We have half z from 0 to 3. This is what is this, 2 minus half, 3 over 2. 3 over 2, I bring it out, so we have 3 over 4 here. Z cube dz. Okay, z cube dz. So this is 3 over 4 z, 4 over 4 z, 0 to 3. So we have 3 over 16, 3 to the 4. Okay, then of course you can find out the solution there. Okay, so this is the integration over a box using Frobenius theorem. For the transformation, for the double integral, we have done the transformation of the coordinates. So we need to find the Jacobian for the transformation. So the same thing for the triple integral case. If we have a function, let's say x, the transformation, let's say the transformation is given as transformation of coordinate. If we have a function x is of x u v w, y u v w, and z u v w. So in this case, we want to transform from u v w coordinate system into x y z coordinate system. Okay, we want to transform from u v w into x y z coordinate system. You need to find the Jacobian. So the Jacobian is given as, so the Jacobian for the transformation is given as the function of x there. So we have x, the function is x y z, variable u v w. So we have del x y z del u v w. Okay, this is xu, xv, xw, yu, yv, yw, zu, zv, zw. So that's the transformation. And due to those transformation, now our integration, let's say over some region R f x y z dv, that we will have integrate over, we have a new region, say phi prime. Yeah, we have here, we have a region here, and then we transform to xy coordinate, we have a new region there. Okay, and here our f becomes, we have f x of u v w, y of u v w, z of u v w, and multiply by the Jacobian del xyz del u v w, okay, du dv dw. So I need to put there du dv dw. So that's the transformation, or the integration for the triple integral, and we do the transformation. Let me give you an example. Let's say we have a transformation. X is rho sine phi cos theta, y rho sine phi sine theta, and z rho cos phi. Okay, let's say we have this transformation. For your info, this transformation, this system of coordinate basic is we call it as a spherical coordinate system. Yeah, the spherical coordinate system. But for the moment, you just accept this. The transformation is given as that. Okay, where rho is the radius of the sphere. Phi from 0 to pi, and theta 0 to 2 pi. Yeah, this is full sphere. Now, with this transformation, if you want to find the Jacobian of that transformation, yeah, the Jacobian is given as we have del x u v x y z x u v w. Okay, this is equal to, so we have x u x v, no v, this is rho, this is phi, this is theta. Okay, let me write again. It's not good. Yeah. Jacobian is given as rho x y z del rho theta phi. This is given as x rho x theta x phi, y rho y theta y phi, z rho z theta z phi. Okay, if you put everything in value there, so we have x rho is sine phi sine theta, sine theta cos theta, x theta is negative rho sine phi sine theta. Okay, phi rho cos phi cos theta, y rho sine phi sine theta, y theta rho sine phi cos theta, y phi negative rho sine phi, z rho cos phi, z theta 0 z phi is negative rho sine phi. I think this is y phi is cos phi, cos phi sine theta. Okay, so if you proceed this, it's not difficult to do that. Just multiply this, all right, and do as we find the magnitude. You will find this equal to negative rho squared sine squared. Sine phi. Okay, so that's the Jacobian for that transformation. So therefore, if you want to integrate the triple integral where our E is given as a sphere, yeah, in this case E is a sphere of radius r, so our f x y z dv, that's equal to integrate over using this transformation. This is a new region, so our f x y z becomes f rho sine phi cos theta rho sine phi sine theta rho cos phi, and multiply with the Jacobian. Remember the Jacobian, we take the positive. Yeah, we look at here. Jacobian, we take the magnitude of the Jacobian. So even though we have a negative, but we take the positive of those things. So we have rho squared, so multiply rho squared sine phi d rho d theta d phi. Okay, that's in general. Let me give you a more particular example. Let's say I want to evaluate this integral dv, where E is given as a solid bounded by this ellipse, x squared a squared plus y squared over b squared plus z squared over c squared equal to 1. Now, and we use the transformation. X equal to AU, Y equal to BV, Z equal to CW. So let's say we have this transformation. See what happens. Okay, so this is from XY coordinate system. This is ellipsoid. Yeah. If you substitute this into the given ellipsoid, what we have our E prime is, we have a squared u squared, so a cancel, so you have u squared plus, for y, b squared cancel out, v squared plus z, c cancel out, w squared, that equal to 1. Okay, so what happened with that transformation? So we have this x, y, z from ellipsoid. You know ellipsoid, like a bola rugby. So we have that. Okay, and we have that ellipsoid. We transform this into u v w. Okay, for UVW, so you have this form, you know, this is the sphere of radius 1. Sphere of radius 1. Alright, so which means for that we have the sphere okay. So this is a sphere, so that if this is sphere, then we can use another transformation using the spherical coordinate, where spherical coordinate that I mentioned earlier in the previous example, we use u equal to rho sine phi cos theta v rho sine phi sine theta w rho cos phi. Okay, and the Jacobian for this, or that before that, we need the Jacobian for this transformation. So the Jacobian for that transformation is given as del x y z del u v w. This is xu xv xw yu yv yw zu zv zw. Okay, if you work out this, you have xu is a, this is 0, this is 0, this is 0, this is b, this is 0, this is 0, this is 0, this is c. That gives you a b c. Okay, so now your integral e dv under the first transformation, you're going to have e prime, your function is just 1, your dv we need to multiply with the Jacobian, so you have, this is your Jacobian, so we have abc here, abc. Now here this is d u dv dw. Alright, to solve this is not easy still, so we need another transformation, this one. So for this, the Jacobian for that is given as, look at the previous example, so the Jacobian is given as rho squared minus rho squared sine phi. Okay, so I move to the next page. So this integral now becomes abc just a constant, so I can put abc outside. Now integrate with respect to e double prime, where e double prime is after the transformation using spherical coordinates that I mentioned earlier. Then we need the Jacobian. Okay, Jacobian is given as, remember that Jacobian is the absolute of derivation of xyz and uvw, so that we have rho squared sine phi d rho d phi d theta. Okay, so now you can evaluate this. Our rho, because the radius is, the radius of sphere is 1, so r, a rho from 0 to 1, your phi from 0 to pi, your theta from 0 to 2 pi, rho squared sine phi d rho d phi d theta. Okay, so if you proceed this, you will have just a minute, you have 4/3 pi ABC. So that's, we give the solution. So you need to do it yourself now. Okay, one might ask, why do we choose this limit? First thing, because for the spherical coordinates, let me describe those things. Spherical coordinate. Okay, for the spherical coordinates, and if I take out the axis, if you consider any point there, x, y, z, let's say point P, x, y, z. Okay, so I put that point here to make it clear. This is P, x, y, z. Okay, this is your rho, where P is on the surface of that sphere. Okay, and this is for x, this is for y, and this is for z. That's z. Okay, so that's rho. This angle given by theta, this angle given by phi. So you can see is any point on the surface of a sphere can be represented by theta, rho, theta, and phi, where your theta from 0 to 2 pi, I mean full circle here, full sphere, and your phi from 0 to 2 pi. So that's why we have a limit of integration here. This is 0 to 1 because the radius of the sphere is 1. Then our phi is 0 to pi, theta 0 to 2 pi. Okay, so with that example, I stop here for this video. Thank you.